Thank you very much, Jeremy. It was awesome. I'm sure everyone has now a lot of questions. If you guys have some questions, you can send them in the chat. Don't forget. So now it's going to be the fireside chat between Jeremy and Izaak. It's going to last for about 20 to 30 minutes. Hopefully, we'll take 1 to 2 questions if we have time, and then we'll go to the breakout sessions. All right, so I'm going to mute myself. If you are, Izaak, are you ready? Yes?
Yep.
All right, awesome. Jeremy, you good?
Yeah. Okay.
All right, so take it away. Thank you, guys.
First off, nice to meet you, Izaak. I don't think we've ever met at a conference yet.
Oh, yeah. Nice to meet you too.
Yeah. Okay. Well, why don't you start by just sort of introducing yourself, what your role is at Coda, and then we'll get into what Coda actually is.
Okay. I'm Izaak. I'm the CTO and one of the co-founders at O1 Labs, and we work on a cryptocurrency protocol called Coda. Mainly kind of what I'm working on day to day is our core cryptography, and in particular, I work a lot on SNARKs. The kind of technology that Jeremy has told us all about. Let's see, what more can I say? Yeah, I don't know.
Okay, sure. That's good. Okay, so Coda, let's pretend it's like a box that's sitting on the table. There's a box that's Bitcoin, it's sitting beside it. What's the difference between these two boxes?
Yeah. So I guess I would summarize it like this. The kind of core idea of Coda is that that of kind of a succinct blockchain. So that is a blockchain where any user on any device, sort of regardless of how powerful that device is, should be able to verify the state of the application. So, be able to verify, the current block height is so-and-so, and the current set of balances is whatever, and my balance is whatever. With Coda, it's possible to do that. So any user can sort of instantly kind of sync to a view of the current chain. Whereas with Bitcoin, in principle, if you really want to sort of, truly verify and not sort of game theoretically verify the entire history, that requires an amount of data and work which is linear in the number of transactions which have occurred so far. Concretely, I don't know, Bitcoin blockchain is like a few hundred gigabytes or something like that. In principle, one would have to sort of download that whole thing and verify it themselves. And the other thing is that because of this fact, one can basically scale up to higher throughput without worrying too much about the verifiability consequences. So one kind of negative side effect, you could say, of increasing the throughput on a blockchain is it makes verification, proportionally more difficult. With a succinct blockchain architecture, that's not the case. Anyone can still verify regardless of how high the throughput gets.
Cool. And the sort of view that I would have as a verified, that's personal to my addresses, or that's like the same view that everyone would have?
So the way it works is you basically get a SNARK which says the current kind of protocol state is whatever. And the protocol state has inside of it an accumulator of the total set of accounts. So in particular, it's a Merkle tree, root hash. And then basically a user sort of queries nodes who are storing the full state for the parts of the state that they're interested in.
Yeah, okay. So it's similar to the SPV protocol kind of in Bitcoin, except for it's also proving that that no transactions were dropped, essentially.
Yeah, you could say that. The other thing that differs, well, so right now we don't have smart contract functionality implemented, but that is something that we're working on developing now. So that would be another difference between the two boxes, as you said.
Sure. And so I imagine that's because you want to make your currency sort of SNARK friendly. Like I'm sure you tweak things at the transaction level, consensus level, et cetera, to make sure that it all comes out nicely in the end. Is that right?
Yeah, so there's a whole bunch of things that you need to do. So you need to have your, first of all, your cryptographic primitives need to be SNARK friendly. because, to get sort of the best efficiency possible for producing these proofs. So like hash functions, signature schemes all need to be snark friendly. That is to say, they need to be efficient to run inside of snarks. And then the other thing is, as you said, the consensus mechanism. So we have developed a consensus mechanism, which is a proof of stake consensus mechanism in the kind of Ouroboros family of consensus protocols, which has the property that you can basically maintain a finite amount of state to adjudicate between forks, which isn't the case with most sort of with all the other protocols in the Ouroboros family, I guess. They require you to sort of look an arbitrary distance back into the past. In our protocol, it's called Ouroboros Samasika. You just hold on to a sort of a finite amount of state, and you can use that to adjudicate between forks. So you don't have that problem in proof of work, where there it's clear you only need a finite amount of state to adjudicate between forks, namely like the accumulated weight of the chain.
Mm-hmm. Cool. And so are there checkpoints sort of in the blockchain, or just like there's a genesis block that I guess is part of the proof, and everything just comes off of the genesis block?
Yep, that's right. Yep.
Cool. Okay, and then so the transactions are it would be like a Bitcoin standard transaction, essentially.
Yeah, they're pretty simple. It's not UTXO based, it's account based.
Okay.
And yeah.
Okay, cool. So you mentioned like full nodes, and so can you sort of talk through what's the sort of ecosystem of who's involved, like
yeah,
who's staking, what are the roles of full nodes, what are the roles of users?
Right. So let me kind of break it up like this. So there's the nodes who are producing blocks, and they are running this proof of stake consensus mechanism. There are nodes who are sort of compressing. Oh, and let me just say about the staking nodes. It's not a closed set of stakers like many proof of stake protocols. It's an open set of stakers. Anyone can stake. You sort of win with probability proportional to your stake. It's similar to proof of work consensus protocols in that way. I shouldn't say proportional to your stake. Let me say with a probability which is increasing in your stake.
Okay. Stake times time, I imagine. So like the amount of time that you stake is also a component?
There's some kind of curve to make some
whatever
property work out of this. It's not that important. Right. So that's sort of an open set.
Okay,
It's
weighted by staking's open to anyone. Mm-hmm. And then in terms of the nodes that offer these proofs.
Yeah. So let me. There's like a few other roles. So and let me say also you can delegate your stake. So you don't need to sort of stake directly. You can also delegate stake. There's nodes who are contributing computing power to actually compress the blockchain. So we actually sort of compress the transaction history in trees. And the reason for this is just that snark proving is pretty expensive. Well, it's sort of not, it's not really expensive in terms of compute cost, just because computation is relatively cheap, but it takes a long time if you were to do it all in serial. Let me say it like that. And so we sort of buffer some kind of history of the most recent transactions so that they can be worked on in parallel, compressed in parallel along a tree. And so the nodes on the network, I guess we call them snarkers or snark workers, can, there are nodes on the network who can do work on that buffer of transactions and be rewarded in fees for performing that work.
Cool. And then the full nodes, they maintain the whole state, and then they use the snarks that were produced by the workers to basically give you a succinct view of the state. Is that right?
Yeah, and so the staking nodes basically kind of fold in these snarks that were produced by the workers into this kind of ever growing, like one snark that stands in for the entire history. And then there are nodes who are holding on to the full state, and you know, the sort of the nodes who don't have the full state can query those nodes for information about particular views on the state.
Cool, cool. And then that folding in process, it doesn't grow, like it doesn't matter how much history has passed, it's constant.
Nope, the entire time, yeah, exactly. There's a constant size proof that just says sort of, there was a big sequence of proofs in, you know, going into the past leading to now, which certify that the current state is whatever.
Awesome, awesome. And then do you have like some concrete numbers you can give people just to sort of think about like how like really rough, like is it hours, or like how long would it take to produce produce a snark, and then how long to verify? And I think you've said somewhere that it's about 4 tweets long, the actual proof itself.
Yeah, so, well, okay, so this is sort of liable to change a little bit, just because we're working on a new proof system now that, you know, will improve on the previous or the current system by quite a bit. But I guess the numbers that as they stand today, and then I can give you a sense of maybe how good they'll get or whatever. Right, so right now it's maybe like 2-ish minutes of computation for a proof that represents one transaction, which sounds pretty bad, except that you can just do them in parallel, and, you know, 2 minutes of computation is like maybe a 30th of a cent or something like that. Yeah, so in terms of verification, it's, you know, well, it's a little bit difficult to give an accurate number because there's efficient batch verification. Let me say the marginal cost of proof verification is something in maybe the 10 to 20 millisecond range. It should be actually, the marginal cost should be quite a lot lower after our new snark system Pickles is integrated. Yeah, and the proof sizes, they're on the order of like, you know, 1 to 10 kilobytes. So that's, you know, a few thousand characters, you could say.
Sure, sure. Yeah, that's cool. Okay. And then if there's anyone who's watching this that sort of wants to get involved, what can they do besides being a participant in the network? Or
yeah, so there's lots of stuff. So let's see. So they can participate in our testnets. That's one great way to get involved, running like, you know, any kind of node. We also have our Genesis program, which is basically, you know, a program where we are kind of building out our initial staker set, and we'll be kind of doing token grants through that to build out the initial community. Drew, okay. I'll respond to that question in a second, maybe. Otherwise, you know, they should join our Discord. We do all of our development in the open on Discord, and also on GitHub. If they, you know, people are really encouraged to make PRs if they want. And, you know, I guess a good way to do that is to sort of drop into our development Discord and maybe ask the team what's going on, or if there's a good way to get plugged in. Yeah, so GitHub, Discord, Genesis program, testnets. I don't know. I guess, yeah, that's maybe a somewhat comprehensive list.
Sure, sure. Did you want to answer Drew Taylor's question?
Oh yeah, I mean, I can.
The one that you saw?
Just,
yeah.
I don't know. I don't know if we want to wait for questions or whatever, but the new snark system is not.
Oh, go for
really
it. Go for it.
Oh yeah, the new snark system is not related to the. It's not directly related to the GPU version, but we should have a GPU implementation of the new snark system too.
All right, and then just out of curiosity, can you tell us a bit about Coda, the company? So your CTO, like kind of what do you do on a day-to-day basis? How big are you in terms of number of people, like that kind of thing?
Yeah, so, okay, so O1 Labs is a company that develops Coda, and I think we're somewhere between 25 and 30 people right now. On a day-to-day basis, I mean, you know, it's varied. Sometimes I'm doing this, sometimes, you know, planning, engineering, priorities, sometimes implementing crypto, sometimes writing blog posts and documentation and that kind of stuff too. Does that give some kind of sense?
And how did you get involved? Like, sort of, were you there at like sort of the start? Was it some ideas that you had originally, or did you join on later? And
yeah. So I started. My co-founder Evan and I started it together. I guess where I was coming from, I was a grad student studying cryptography, and I learned about SNARKs from Alessandro Chiesa, and he's one of the kind of early people in the sort of new wave of SNARK development, and it just seemed like a really sort of this, I don't know, the concept of verifiable computation was very compelling to me, and it had this clear application. So that's kind of where it started.
Awesome. So another question from the chat. Do you have any plans on when you develop a mainnet or deploy a mainnet, what are the tokens? How are you going to distribute the tokens?
I don't think we have any, beyond the Genesis program, I don't think there's any public determination as of yet about like what the initial distribution will be, but I would say stay tuned.
Yeah. Okay, cool. And I'm just looking for inspiration for questions. So so you talked a bit about how people can follow the project, and then you personally, you have like Twitter, you're on social media.
Yeah, I am on Twitter, except that I am badly addicted to it. And so I've changed, well, I gave someone my password. So I don't know my password, someone else has it. So if I don't reply, that's why, but I'll probably relapse at some point. But yeah, it's Izaak Meckler on Twitter.
Okay, and then I'll jump back a bit. So let's say that I wanted to take your sort of approach and apply it to, say, Bitcoin for whatever reason. Like what would the challenges be for, like, just to throw up a node with a zipped up version of the Bitcoin blockchain and then give people like little proofs about what they want?
Yeah, the main challenges are just making it efficient, given that none of the crypto in Bitcoin was chosen to be efficient inside of like SNARKs that you can do recursion with. I don't think it's insurmountable. It would definitely be a lot of work, and you would need like a big improvement over the state of the art. Other challenges I think have to do with the fact that ideally you'd want some kind of mechanism for continually compressing the history. Maybe you do it on a basis, enough of a basis that you can sort of do it yourself. But in Coda, that's kind of all integrated into the system. There is the system, mechanism for incentivizing system participants to perform this work of compressing the history. So, yeah, I guess.
Yeah. So I guess the incentives is a big piece. If you don't, no one has an incentive to do it, and you have to build that in at the currency level itself. Okay, let me just go through the general questions here. I think we answered all of them. Arthur, do you have any further questions?
Yeah, actually, I think we had actually a question from Crixus. Wait.
Oh yeah.
I'm trying to find it. Aside the wonderful flow in implementation of the technology used, what unique real-life application can I use it for as a normal user, not as a node owner on mainnet launch?
Yeah. So I mean, on at mainnet launch, it'll basically be value transfer, and that is potentially going to be with not just the Coda currency, but like tokens on top of it as well as kind of limited programmability overpayments. Further down the line, I mean, once kind of more smart contract functionality is implemented, the kinds of ideas that, I mean, I think overall, like, I guess, let me say it like this. I think in an ideal world, like all of computation would be like in one, you know, big, all of the world's computation would be sort of recorded in one big snark on some public state. And then if you wanted to know anything, you would just sort of get that one snark and then look at the part of the state that you were interested in. And so, for example, you know, in that world, you would be able to, you know, you'd be able to do things like, well, okay, so this is sort of an example that I have gone to many times, but let me just say it for if, I guess there's no harm in repeating yourself. You know, when a user, oh, sorry.
No, yeah, go for it. Just repeat yourself.
Okay.
It's always good to repeat yourself. It's just like
Yeah.
to make an idea stick. Yeah. So that's good.
Yeah. So for example, you know, it's a very common practice, sadly, for lenders to make racist loan determinations. And so you might, you know, you might want to have some kind of mitigation on that. Maybe you want to have some kind of oversight body, be it, you know, a regulatory body from a government or some more decentralized regulatory sort of oversight body, inspect and kind of sign off on what the loan determination algorithm that a particular lender is using. And of course, you know, that's a very contestable question of, you know, what is sort of a less biased lending algorithm. It's really quite hard to say, and it's a political question. So, but assume, you know, we have to answer that question, right? We do, in terms of like just deciding what we're going to let a lender use. And so, but once that decision is made, you really want to hold the lender to that. Once they, you know, once the regulator signs off on the algorithm A, you want to make sure that every time that they send a loan determination to a user, that really they're cooperating with their stated policy that was approved by the regulatory body that we all trust, or some of us trust. And you know, so for that, you sort of want to have this public state where a user can sort of look up, okay, what is the policy? What is the SNARK verification key, basically, that I'm supposed to check the lender's claimed loan determinations against? And then, you know, when I ask the lender, hey, you know, here's my financial information, can you produce a proof? Sorry, can you give me a loan determination along with a proof that you actually produced that loan determination using the policy that was approved by the regulators? Then they can do that. They can produce a proof that says, I used the policy that was approved of by the whole committee to make this loan determination. Whereas if you didn't, you know, force them to produce that proof, then very likely they'll, you know, show one thing to the regulatory committee and then go and do another thing in practice, because there's no way to hold them accountable. So those are the kinds of applications that I think are sort of have long-term, really powerful potential in terms of building software that it's possible for users to have some accountability over.
Right. Makes sense.
So I thought of a few questions actually while you're talking. So the first thing, I guess, when I think of SNARKs, I automatically go to, you know, zero knowledge, and I think of privacy. But in this case, so Coda's privacy model is basically the same as Ethereum. Like you can see a full state, it's pseudonymous. Is that right, more or less?
Yeah, yeah.
And then
yeah,
if you wanted,
sorry, go ahead.
Yeah, well, I was going to just ask if you see any vision to sort of combine maybe like some privacy features on top.
Yeah, you totally could do it. I mean, the easiest thing to do would be to have like confidential transactions where amounts are hidden, but like the graph is not hidden. Mm-hmm. That would be pretty straightforward. It's definitely a lot harder to see how to do a Zcash style thing because you know, the history kind of, I mean, it's just sort of unclear exactly what you gain because the history grows linearly with time. So I mean, I guess the sort of verifying nodes won't have to see that whole history, but or hold on to that history, but the consensus nodes still will, right? Whereas with Coda, they just sort of hold the current UTXO set rather than the entire history of it.
Right.
Anyway.
Right. And then a similar question. So if you want to expand to more verbose smart contracts, obviously the state of the contract is a little more complicated than the state of a balance of an account. But is it really that insurmountable, or is it, how hard would it be?
No, I mean, you know, there's sort of no reason. I mean, let me see. You could just sort of in a straightforward way just sort of do Ethereum style smart contracts and state management and all that. You know, you would still have the same problems of the potentialities of the state growing in an unbounded way, but yeah.
Yeah. Okay. Question from the chat. So obviously in Zcash's case, they had a trusted setup. Is that something that you'll have?
So it's kind of interesting. We don't have to, in a sense.
You're not ZK, right?
Say again?
Because you're just a snark and not a ZK snark, or is it?
No, it's actually because, yeah, it's actually because, so, you know, basically all of these snarks sort of, if you look a little bit under the hood, all of this sort of at least new generation of snarks, which have universal trusted setups, the reason, let me say it like this, they all inherit their trusted setup from something called the polynomial commitment scheme that they use. If you really want a snark, a succinct verification proof, you basically need to use this polynomial commitment scheme called the KT scheme, or KZG.
I just have to interject that I did my PhD at Waterloo, and so Aniket and Greg, who are the two people that worked on that with Ian Goldberg, I was like sitting right beside them when they came up with that scheme, which was really cool. And then it was like really cool from the start, and like but it didn't get a lot of tractions. And then, you know, because that came out like, I guess like growth and like people were working on snarks, but it didn't have the branding of snarks. And so now it's like 10 years later, and all of a sudden everyone is in love with it. But anyway, sorry.
Yeah. So they all inherited from this polynomial commitment scheme, which requires a trusted setup, but it's universal in the sense that it works for all programs, you could say, and it's also updatable. So like if you want, you can sort of keep contributing randomness to it over time. But that's all to say, if in the specific context of doing recursion, you can get away with using a polynomial commitment scheme which is not quite succinct, which is sort of, I don't think anyone really came up with a word for it, but sort of amortized succinct. And that sort of polynomial commitment scheme, for example, is furnished by the inner product argument that I guess goes back to this paper of Jonathan Boodle and maybe other people, and then is in bulletproofs and so on. And you can use that instead. The performance is a little bit worse. So for efficiency, we will probably end up using the KT polynomial commitment scheme, at least in one place. But as sort of the efficiency of the overall proof system improves and so on, then there's no obstacle to switching to the no setup version.
Cool.
We also, if efficiency in the next couple months, if it gets good enough, we might just go with the no setup version too. But
right. Okay. So I'm out of questions.
All right.
I'll throw it to you, and then.
All right. Well, thank you very much, guys. It was super cool to watch you interact, and thank you very much, Izaak, for your time. So the kind of part 2 of this meetup is over.